morning, everyone. My name is Howard, and I just finished my third year as a math specialist and computer science specialist programs here at UP. And it's my great honor today to talk about how to gain intuition behind analysis with the lens of learning the math language. So, first of all, I'd like to express my sincere thanks to the event organizers. Not only to organize this successful event, I hope you guys enjoyed Toronto last night. It is the correct amount of time for you guys to experience the positivity Toronto has to offer, because just a little bit longer, you might experience something else. But anyway, I hope you guys liked it. And actually, due to some miscommunications and things like that, my talk got rescheduled from Tuesday to today. So really thank you for the organizers for doing that, and also thanks everyone for coming and for coming again. I will try my best to not let you down. And so as the title suggests, it will not be as a technical talk as like some of the other talks that we've seen so far. It's mainly about something that I personally use, and it is my goal to make the analogy from natural language to mathematics language, and trying to provide the intuition for some of the abstract concepts that we encounter in analysis in general. So after I mentioned that, basically, everyone's first question is like, why do we talk about language in the first place? What are some similarities between the natural language and the mathematical language? And I'm going to explain on a philosophical level of the similarities between natural language and mathematical language system. And then we'll establish our framework. It's basically analysis review 101. We'll review stuff from the basic structures of R. We'll talk about the order of R. We'll talk about functions. We'll talk about differentiation, integration. It's mainly trying to provide the intuition across all levels of elementary analysis, from fundamental axiomatic level to a little bit in-depth level, such as differentiation, integration, and a little bit of the bag measure theory, actually. And so we'll see a lot of good examples of why this sort of natural language analogy is going to work in terms of establishing results, remembering results, establishing proofs and stuff. But there are things that this theory doesn't capture. And what I will analyze in this section is a good section, is to try to find some things that the theory has flaws in, I haven't thought it through, or if there's anything that the theory doesn't provide a good intuition. And I'll briefly talk about future, and then we'll be for questions. Okay. So the first question, why language? I have provided 3 examples of languages: the natural language, the programming language, and the mathematics language. So as human beings, we first use natural language. We develop natural language as a medium of communication. And then we try to develop the mathematics language. In fact, the origin of mathematics language is a great debate of philosophers. So some of the people think that mathematical system is really a rigorous and beautiful system. It couldn't be something that human beings developed and invented. It should be something that's already there, and we went there and discovered it. This, I disagree. I think mathematical language follows very intuitively from our daily experience of counting. And I support this theory. So mathematical language and mathematical system is a vast simplification of our natural language system, in the sense that it is a complete formal system, and it's completely formal everywhere, in the results, in the logic, and in everything that develops. So there are formalism actually observable in natural language as well. We can see there's called context-free grammar, or a parse tree, that lets you to break down a sentence into different sentence structures, grammatical structures, syntactical structures, and things like that. So there are formal areas of natural language. And in fact, it motivates the start of a field called symbolic AI, where they try to use a very large corpus, probably every possible word on Earth, and then they have a complete set of rules, they hope, and then try to generate using context-free grammar and parse trees to provide natural language understanding. Look how that turned out, right? We are using deep learning. We're not using the symbolic AI anymore, because the natural language has more to just formal systems. First of all, it has logic built in. Obviously, mathematical system also has logic. So the mathematical proof is trying to use logical deductions to develop truth statements based on an already known set of truth statements. And that's what mathematical proof and logical deductions is all about. And that's what we learn as a mathematician, right? But besides formalism and logic, there's still something else that we need in order for natural language understanding and to make meaningful conversations. And this is called psychologism. In fact, we need some understanding of human psychology, in fact, to make meaningful conversations. I summarize this as 3 questions. Basically, when we're having a conversation, we need to understand 3 things. Where this conversation is leading us, where this conversation is going, basically. And how is this conversation changing? If I want to deliver some information, for example, how is your feeling changing? And what are some information present in this conversation? And this aspect is not present in mathematical language. It's not present in programming language either. So what I'm trying to do is to map back the math language to gain intuition using this psychological daily experience that we experience, we use basically every day in our natural language communication. And this is how it motivates. And so let's establish the framework. In fact, in the first few classes of first year calculus, we tried to axiomatically assume some structure about the real numbers R. The first of which being the 8 axioms saying that R is a field. There's identities, inverses, multiplication, additions. It is very intuitive to think of sets, as alphabets. And alphabets generally is words generally sentences. But R is closed under all sorts of operations, meaning that the mathematical language is very simple. The words are the alphabets. The sentences are the words. So with this, we can start to talk about some order. We develop the positive numbers, meaning making R into an ordered field. We develop the absolute value. And this, in fact, corresponds to positive emotions and negative emotions intuitively as well. Then, the final assumption is that R is a complete field, meaning that every bounded set has supremum and infimum built in. It's basically the same thing as saying every Cauchy sequence converges. It's the same thing. But we have this assumption, and it follows intuitively with the emotional intuition that we have for R. With definition of R, we can define several subsets of R. Some sources define natural numbers first as an inductive subset, then integers, and then rationals. And you can define integers, and then rationals, and then natural numbers just as integers that with absolute value themselves. Okay, this is just a framework, just a starting point. And what matters in analysis is when we start to analyze functions. And in fact, in our natural language, in our daily communications, we have conversations all the time. And most of the conversation is one input, one response conversation. I said something, you say something. And this is exactly the idea for functions. Right? You have your emotional response for every input that I make. You cannot have 2 responses at the same time. And so if we record the emotional values, we get functions. We have one-to-one conversations, meaning functions from R to R. We have group-to-group conversations, probably, so meaning functions from Rn to Rm. And in fact, so if a group of n people is saying something to a group of m people, each of the n people's response is going to depend on all of the n people's inputs. That's just how conversation goes, right? And this motivates the concept of component functions. If we just think of one person's response instead of all of the n person who's in charge of responding in this conversation. And if you record like emotional flows and stuff, you can sort of have an idea of what this conversation looks like. Either it goes downward and upward, and where it oscillates, or it just keeps increasing. You just get more and more excited, that basically means. And the composition of function is just very intuitive. I say something to you, you say something to another person, right? That's composition. We constantly have composition in our daily lives, in our daily communication. Okay?